Now, adding and subtracting vectors is going to be very similar to adding and subtracting matrices, which you've already done. Especially if you think of your vectors as column vectors, you're just going to add the corresponding parts and you'll see what happens. With a diagram, as far as what it looks like when you're adding and subtracting vectors, we're going to say that the vector W, which goes from A to C, is going to be the same as if you added the vectors U plus the vector V. Now, in real life, if you were traveling from A to C, W would be the quickest way to get there. But as far as vectors are concerned, if you are going from A to C, you can get to A to C by going there directly, which is by vector W, or you could get there by going to B first and then going to C. You'll end in the same place. So when we add vector U and vector V together, we get vector W. Now, just thinking in two dimensions, does it make sense that U looks like we're going, you want to say over 3, up 3? Are you okay with using that as an estimate? Now, if that's over 3, up 3, does V look like you're going over 3, down 2? And then vector W, what have you done? You've gone over 6, up 1. And can you see if you add the corresponding elements of those two column vectors? 3 plus 3 would be 6, and 3 plus negative 2 would be 1. And that's the idea of adding vectors. So this would be our vector equation for this. Going from A to C is the same as going from A to B and then going from B to C. We call the answer to a vector equation, vector W, we would call that a resultant. Some important things that we're going to see for adding and subtracting vectors is that if you have a vector AB, which is the vector U, going from B to A is the exact same distance, but just in the opposite direction, so that would be negative U. Again, I can put arrowheads over top of these to make sure we see that those are vectors as well. So it's the same vector, has the same length, but it's just in the opposite direction. So if A is equal to 2I minus j, and if we write A over here as a column vector, it would be 2, negative 1. And B as a column vector would be negative 1, comma 3. What we could do is we could draw, what does 2, negative 1 look like over 2, down 1? What does negative 1, 3 look like over 1, down 3? This is my vector A. This is my vector B. So graphically, if I wanted to add A and B together, I would take A, start it anywhere, it would go there, and then where I end up and I add B to it, would start there and there. My resultant for A plus B is right here. That's graphically. Graphically, we can see that the answer is going to be 1 to the right, 4 down. Algebraically, A is 2, -1, and B is -1, 3. Oh, I drew B wrong? Nobody said anything? Sorry, I got to erase B. I just realized I drew it wrong. Still not. Here we go. Go away. There we go. So B, -1, which goes this way, up 3. This would be B. Here's my vector B. So if I took vector A, which ends up there, and then I took vector B, and where I ended up went there, this would be my resultant, which is over 1, up 2. And if we wrote out A and B correctly, like we should have, and drew it correctly like we should have the first time, you can see that if you add those corresponding coordinates together, you'll get 1 and 2. Similarly, if I took B, there's my vector B, and then I took -A. So -A would be this one, but our arrowhead would switch to the other side. Whoa, that's crazy. And put those together. There we go. That's where it would end up. What's going to happen as a resultant? It's going to end up over there. As far as the diagram shows, our resultant is -3 and up 4. Algebraically, what does this look like? Well, B is -1, 3, subtract A, which is 2, -1, and you can see that -1 subtract 2 is -3, and 3 minus a -1 is 4. Finally, if you took 2 B's, there's 1 B, 2 B's, and then added 2 A's to that, 1 A, 2 A's, there would be a resultant. And algebraically, you would get a resultant of 2, 6, minus 2 is 4. And you can see that from the diagram as well.